Alright. Inductance. So, this very basics of inductance is Faraday's law, which is just EMF is equal to negative d phi dt. So this is for example, if you have a coil of wire with some B field going into it, and it's just a B field all around. And then let's say this B field is increasing. So you just do negative a dB dt. So usually you'll be given dB dt, you'll be able to figure it out somehow. And you can of course figure out the area of the coil. And then EMF is just that magnitude. And then for direction, you use Lenz's law, which just tells you, all it tells you is the direction. So for this example, I'm going to draw another view rotated. So now the coil is like so, and our B field is going like so. Let's say B field is increasing. In that case, if we use our beautiful hand here, so d phi dt is, none of those are what I want. Okay, rotate. So d phi dt, change in flux over time, is pointing downwards. Lenz's law says you should flip it 180 degrees. So you're going to turn your right hand back around. So now it's facing up. And now your fingers will tell you the direction of the induced current. So let me draw this so hopefully you can kind of tell what's going on. So that backside is like behind all those arrows, and then the current will be going like so. Alright, so that is the basics of induction. So that's the example of a coil with a changing B field. Another common example of basic induction would be your sliding bar. So here you have a set of conductive rails with a conductive bar sliding along them, and it's all in a B field. So I guess the coil is the classical example of changing B field. Here's the typical example of changing area, but the end result is the same. You change phi or flux. So let's see. So I suppose there's two different ways, or two different types of sliding bar questions. One is, let's say the bar is given a velocity. It's constant velocity v. And I'll ask you, what is the current through the wire? So I guess for that you need a resistor here, some resistance R. So B field strength B. So we just have to figure out what is R d phi dt. Well, that is going to be what? So B field is constant this time, so we're just looking at dA dt. And then that is just going to be, if we call this L, that's just BL dV dt. So this is our EMF, or magnitude anyways. I dropped a negative sign, but really the negative sign is just there in spirit. You figure out the direction with your hands. So that gives you the strength of the EMF. So if we want current, I equals V over R, is that over R. Alright, so now you want to know what direction. So one thing you can do is Lenz's law. So I will draw this again from a different angle. Then of course we have this. Alright, so B field is doing this. Alright, so here, if we use our amazing hand, use copy, paste. So dphi dt, since area is increasing, dphi dt is going to be the exact same direction as v field, like so. And then Lenz's law says we need to flip our hand. So then you end up with this hand, and that gives you direction of current being this way. So current is going to do this. So through the bar, it's going to be flowing up. Another way of looking at it is you can imagine you're looking at a tiny chunk of metal on the bar. And if you look there, you have a bunch of charge in the bar, which is moving with some, here, let's say you're just looking at a particle in the bar. You have a bunch of charge in the bar that's moving to the right with some velocity v in a B field which is pointing down, or into the page rather. So then you can just do the whole F is equal to QV cross B. And if you do that cross product, that right-hand rule, you'll find that the force is up, which would suggest a current up. Same answer as we got using the other right-hand rule. Alright, cool. So that is the sliding bar and the coil done. Now we'll take a look at the actual thing called inductance. So this is used in circuit analysis. Inductance, symbol L, is defined as EMF over di dt. So it's potential difference per change in current. So I guess now that we're moving on to circuit analysis, conceptually, inductors are analogous to capacitors, right? You have capacitors which oppose change in voltage. Inductors oppose change in current. So let's see. So inductors in a circuit are going to be drawn like this, just a bunch of curly-doos, and well, they do what they say on the tin. So let's say we have a circuit that looks like this. Right, so there's a switch, and then we have this. Alright, so there's some inductance L, there's some resistance R, there is some EMF epsilon. So so if you remember with capacitors, at time 0, a capacitor acts like an open circuit, or a closed circuit rather. And at time infinity, it acts like an open circuit. The inductor is the opposite. At time 0, it acts like an open circuit. And at time infinity, it acts like a closed circuit. And if you think about the idea of an inductor opposing change in current, that kind of makes sense, because at time infinity, you're not going to have any change in current, so of course it's going to not do anything. Yes. So let's say this this switch just closed. What happens, or what is the current flow at time 0? So we could redraw this time 0. Effectively, it is going to act like this. because it's opposing all of that new current this battery is trying to introduce. So it's just going to stop it all. At time 0, no current at all. Alright. Then what happens after a long time? Well, then we will redraw with a closed circuit. So it's just this picture, and we'll find I is equal to epsilon over R. And then as for what happens in between, then we can use the definition. Epsilon is equal to, let's see, should be L di dt. If you just rearrange this equation here. Did I do that right? Yes. Okay, cool. So then we combine that with the other equation. Oh, why is this all jumbled up? No? This one wrong? Here, let me pull up the AP formula sheet. Okay, let me just double check. Epsilon is equal to, I guess, okay, there's supposed to be a negative sign there. Alright, cool. So, working with this, then, if we look at our original circuit, the other thing going on here is there is a resistor. So we can also say, okay, hang on, before we move on, I'm going to define positive current as this direction, just so we don't get confused. So then I'll also be changing that to sub battery. And then the other equation we have is that I is equal to V over R, just for the resistor. So now, let's see what happens. Alright, so we should hopefully be able to just stick these together if I've done this right, because yes, so then epsilon from the inductor plus the voltage from the resistor, which is going to be IR, needs to equal epsilon battery. So then we can sub this in. Okay, I'm back. Alright, so derivation aside, current, you're going to end up with this. I don't know. And this kind of, if you graph this out, it's going to look like this. Right. Let's see. Is it? Yeah, it's going to look like this, which checks out because we have zero current to begin with, and then over time it is going to increase to its maximum. All right. Then
Andy, I think the only thing you did wrong was like it should be 1 over I. IR should be on the bottom, so you take the natural log of it. You see what I mean?
whereabouts? How does IR end up in the bottom though? I know it should be there, but
Like so you do E battery minus IR equals L di dt. Then you move that to the other side. So it's 1 over E battery minus
oh
IR.
no, I see. I see what you're saying. I integrated it the wrong way. Good catch. Good catch. Okay, so this go away. Alright, so then, I suppose, yeah, I still need that. Is equal to E bet minus IR over L, and then we'll rearrange. dt. Well, I suppose one. Alright, whatever. Integral, yes. And then we will end up with okay, let me change this little r or little I. And then we need an L over R here is equal to T. Yes. Okay, then we just raise both sides, or rather, I guess we'll multiply over some stuff first. So we end up with minus IR is equal to e to the R over L T. Lost a sign. That's right, this is supposed to be negative because we have a negative IR inside there. So there we are. And then so then if we solve for current, we'll find I is equal to negative I over L T plus epsilon delta, or rather, I guess we do it the other way around. Battery minus e to negative I over L T 1 over R. Okay, sorry about that. Okay, looking at this, actually, don't do that. We're still off by a little bit. Whatever. Unless, yeah, no, I don't know. I don't know. We're a little bit off because if we factor out a v over r here, then we get 1 minus 1 over v, which is not supposed to be there. So there's, I don't know. Ignore this, but that's the gist of the derivation anyhow. This is the equation we'll actually need. If on the AP they make you derive it, they should hopefully, they will guide you through it a bit more. So you should be able to figure it out from there. Let's see. Okay, right. So then from there, next thing I suppose is energy of an inductor. This is just something that can pop up every once in a while on a circuits problem. It's just 1 over 2 L I squared. So, I don't know, hopefully this is pretty easy to remember. It's the same form as, for example, for a capacitor, you have 1/2 CV squared. So yeah, that is energy of an inductor. That can also be used in, for example, LC circuit problems, if it's asking for maximum current flow or something like that, because you know all of the energy will be in the inductor.
I know it's on the not on the test, but can you do like a 2-second explanation of like the Maxwell's equations? Because I just want to know.
Okay, so first one, okay, there's supposed to be dots in here. That is important. But anyhow, so first one is just a how do you say, a restatement of Gauss's law. So this is just saying charge enclosed will give you the E field like emerging from a surface. So this is just like, I guess one way to say it is this is all written in derivative form. A lot of the stuff you've learned already in integral form. So there's Gauss's law, integral of what? E dot dA, yes, is equal to Q enclosed over epsilon naught. That's the same thing. And then this one is just saying there's no source of B field or no sink of B field. So if you take in multi, this is saying divergence of B field is 0. So if you were to draw a graph of B field, you can never have something like this, right? Because now you have a source at this point here, which, I don't know, that should coincide with what you've done so far. B fields always tend to look like loops one way or another. So this is just no source of B field. Now, next one, let's see, curl of E field is equal to negative d phi dt. So that one is just Faraday's law, which says, what is this? D phi dt. So, I mean, Faraday's law works just fine. It's just that you have to use your hand to figure out the direction. And I guess technically you need a surface. So Maxwell's equation for this is just like a generalization of that. And then this one I think is the one you guys covered more extensively in class. So this one is covering what? B field from a current. So this term here is B field from current, which is just B is equal to mu naught I believe. Yeah, okay. And then this term here is the new one, which you shouldn't have to touch, but it's just B field from a changing E field. So the example is if you have two capacitor plates and it's being charged, there is gonna be a B field created in this gap. Alright. So that's Maxwell's equations. Alright. Anything else?
Andy, I had some questions on, so our latest worksheet talked about symmetry in Maxwell's equations. Could you explain that? I don't really understand it very well.
Alright,
And Andy, do we
so
need to know displacement currents for the AP exam?
no, absolutely not.
Okay, thank you.
Yeah, because like these first three equations you've already learned. It's just this part here that you haven't already learned in some other form. And that one does not appear. So do not worry about it. Three kinds of apparent lack of symmetry in Maxwell's equations. General lack of symmetry. Okay. So first one says quantities epsilon naught, mu naught only appear in two of the four equations. So let's see. So I guess there's no epsilon naught or mu naught in this second equation here, but that's kind of like, I don't know, there totally could be a mu naught or an epsilon naught there, but it's next to a 0, so no one cares. And then for this one, I guess simply put, you already have a mu naught incorporated in there because you have a B field. I don't know, that's how I see it anyways. I'm not sure if that's necessarily right. Then what next? There's a minus sign for Faraday's law, but not for Ampere's law. Which one is supposed to be Ampere's law? Ampere's law, that's the last one. Okay. So minus sign for Faraday's law. So that is saying if you have dB dt like so, then you would have an E field like so. Or, yeah, more or less. That's what it's saying. Whereas the last one, Ampere's law, is saying if you have a this is current or dE dt, then you will have instead a positive direction, so like so. So the question is, why is there an asymmetry there? But I don't know, this kind of makes sense, because if you, so let me draw this picture a little bit better. So in the left case, what I'm saying is this: if the arrow is dB dt, and then the circle is E. But then if we, I don't know, if I like zoom in on this part of the picture, so now we just have B there, and we have E there, dB dt, E. Then if we then use this one, just kind of like shove it in there, don't think too hard about if this is actually allowed or not, then you would find the B field is going around this way, which checks out because where it touches the other B field line, the dB dt, they're pointing in the same direction. So really, the way I see it, that negative sign being on just one of them is just a fact of how geometry works, how the cross product works. Because I think you've like undone a cross product. You've like done a cross product backwards in one of them compared to the other. So you have to insert a negative sign. Alright, then last one, missing magnetic pole terms for Gauss's law for magnetism and Faraday's law. So, what is Gauss's law for magnetic pole terms? What is it even talking about? Magnetic pole terms. Is it saying for an isolated magnetic pole? So I'm assuming what it's saying is it's not accounting for, like, the way Gauss's law for E fields works. You have Q enclosed over epsilon naught. I think what this is saying is Gauss's law for magnetism just says 0. There is no, I don't know, magic B enclosed or something. And well, I mean, that's kind of just a consequence of the second Maxwell's equations, that B field can have no source or no sink. If you have a magnetic pole, then you would have to have B field being generated or like deleted there, which is just not how the B field works.
Thank you.
All right. Anything else?
Let's say you just like were mentally locked out of this entire worksheet.
Uh huh.
Is that fine?